Hi everyone. In this video, we are going to discuss about another example of Smith chart. The given example is find the location and length of a stub matching for a transmission line having characteristic impedance 50 ohm and terminated with 105 plus J 40 ohms using the Smith chart. Now coming to the solution, given that the characteristic impedance Z0 is 50 ohms and load impedance ZR or ZL is 105 plus J 40 ohms. So determine location of the stub and length of the stub matching for a transmission line. First determine normalized load impedance. We know that the normalized load impedance Z suffix small r is equal Z suffix capital R by Z0, where Z suffix capital R is the load impedance. Given that the load impedance ZR is 105 plus J 40 ohms and the characteristic impedance Z0 is 50 ohms, 105 divided by 50 is 2.1 plus J 40 divided by 50 is 0.8. So we know that the normalized load impedance is a complex quantity. It has both real parts and imaginary part, and the real part of the normalized load impedance is resistance and the imaginary part of the normalized load impedance is reactance value. Now here the resistance value is 2.1 constant circle and reactance value is 0.8 constant circle. In the Smith chart, mark the intersection point of 2 is equal r is equal to 2.1 constant circle and x is equal to 0.8 constant circle. And this is the Smith chart. So in this Smith chart, we have observed that there are different constant circles. R is equal to constant circle, and there are different x is equal to constant circle. And this is the horizontal axis. This is the horizontal axis, and this is the center point. The center point is 1, 0. And this is the center point. The center point is 1, 0. So this is considered as point O. So above the horizontal axis, this is the horizontal axis. Above the horizontal axis, it has the positive reactance value, and below the horizontal axis, it has a negative reactance value. So in this Smith chart, mark R is equal to 2.1 constant circle and X is equal to 0.8 constant circle. And this is R is equal to 1 constant circle, R is equal to 2 constant circle. Now here what is the resistance value? The resistance value is 2.1. So the resistance value is 2.1. So this is R is equal to 2.1 constant circle. R is equal to 2.1 constant circle. And what is the reactance value? X is equal to 0.8. X is equal to 0.8. And this is X is equal to 0.8 constant circle. And this point is the intersection point of R is equal to 2.1 constant circle and X is equal to 0.8 constant circle. This intersection point is considered as a point P. This intersection point is considered as a point P. So what is this point value? 2.1 constant circle plus J, X is equal to 0.8 reactance circle. R is equal to 2.1 constant circle, X is equal to 0.8 constant circle. Connect center point and point P, and after that draw the VSWR circle. How to find out and how to draw the VSWR circle? Center O as the center point and OP as the radius. O as the center point and OP as the radius, and draw the VSWR circle. Draw the VSWR circle or constant circle, and this is VSWR circle. This circle is called as voltage standing wave ratio circle or constant S circle. This VSWR circle or constant S circle intersects the horizontal axis to the left of the Smith chart and to the right of the Smith chart. And this is the left part of the Smith chart and this is the right part of the Smith chart. The VSWR intersects right part of the Smith chart. This is the intersection point. That intersection point is considered as point M. Point M is the intersection point of horizontal axis and VSWR circle to the right of the Smith chart. From center to the point M, the distance is, and this is 2.5. 2.5. From center to point M, the VSWR value is 2.5. And this is VSWR value. Now here the VSWR value is 2.5 approximately. Next, second step, determine VSWR value. So from the Smith chart, the VSWR value is, the VSWR value is OM. So OM is approximately 2.5. Next, determine normalized load admittance. The line opposite to the normalized load impedance. This line cuts the VSWR circle and this is the crossing point of the VSWR circle. This crossing point is considered as a point Q and this line OQ line OQ line OQ is extended. That extended line cuts on the outer circle of the VSWR. So this is the outer circle rim of the VSWR. This crossing point is considered as a point Q dash. At point Q, find out R is equal to constant circle and X is equal to constant circle. And this is 0.4 and this is 0.5 and approximately this value is 0.41. So at point Q, the resistance value is 0.41 constant circle, 0.41 constant circle. Plus, and what is the reactance value at point Q? The reactance value is at point Q and this is 0.2 and this is 0.1, 0.158. So now here the point Q is below the horizontal axis. So below the horizontal axis it has a negative reactance value. So minus J 0.158. So from the Smith chart, the normalized load impedance y suffix small r is equal at point Q 0.41 minus J 0.158 0.158 at point Q. Next, determine admittance value. How to find out the admittance value from the Smith chart? So first mark the point T. The point T is marked as out the admittance value from the Smith chart. So first draw the intersection point of VSWR circle and M as the center. Draw the circle M as the center. M as the center and draw the circle. So this circle cuts the VSWR circle This intersection point is considered as point T. At point T, identify r is equal to constant circle and x is equal to constant circle. So r is equal to constant circle at point T is 0.9, 0.9 or approximately 1, 0.9 plus j and that is the reactance circle 0.95. At point T, identify r is equal to constant circle. The r is equal to constant circle is 1 and reactance value is approximately 0.95. At point T, 1 is the constant circle, r is equal to 1 constant circle and the reactance circle is 0.95. At point T, from the Smith chart, at point T, the admittance value is y is equal 1 plus j 0.95. That is step number 4. First, determine location of the stub on the transmission line from the load. How to calculate the location of the stub on the transmission line from the load? The line OK, and this is the line OK. This line OK is extended on the outer circle rim. That outer circle rim crossing point and the extended line OQ is considered as a Q dash. The location of the stub on the transmission line from the load. So from the Smith chart, the location of the stub on the transmission line from the load can be determined as first extend the line OQ. The line OQ is extended on the outer circle rim. That outer circle rim cutting point is considered as point Q dash. So this point is considered as Q dash and the line OT is extended using scale. The line OT is extended on the outer circle to the point on the outer circle. So that extended line cuts the outer circle rim. That crossing point is considered as a point P dash. Cuts on the outer circular rim. That crossing point on the outer circular rim is considered as a point T dash. The distance Q dash, and this is the point Q dash, and this is the point Q dash, and this is the point T dash. The distance Q dash T dash measured on the wavelength scale towards the generator gives the location of the stub. Step number 5. So determine location of the stub on the transmission line from the load. So that is denoted as L suffix S. So from the Smith chart, the location of the stub is Ls is equal 0.5 lambda minus at point Q dash at point Q dash the value is minus 0 and this point Q dash is below the horizontal axis, so it has a negative value. So that is 0.7 minus 0.47 lambda, and this is the point T dash. At point T dash the value is 0.16 lambda. So the location of the stub on the transmission line from the load is denoted as L suffix S. L suffix S is equal to 0.5 lambda, and this is the left side end of the Smith chart, and this is 0.9 and this value is 0.49 and 0.5. So LS is equal 0.5 lambda minus 0.47 lambda, 0.47 lambda, and 0.47 lambda, that is a point q dash. That point q dash is below the horizontal axis, so he has considered negative sign, minus 0.47 lambda plus 0.16 lambda. So therefore LS is equal to 0.19 lambda. So from mark 0.19 lambda in Smith chart. So Q dash and T dash, the distance Q dash T dash is measured on the wavelength scale towards the generator, which gives the location of the stub. So that is LS is equal to 0.19 lambda. Calculate the susceptance of the stub from the Smith chart. How to calculate the susceptance of the stub from the Smith chart? The susceptance of the stub is equal to the negative value of the susceptance at point T. So in Smith chart, this is the point T. At the point T, okay, what is the admittance? Admittance is equal to conductance plus susceptance, and real part is conductance and imaginary part is susceptance. So now we are at point T, the conductance value is 1 and susceptance value is 0.95. The susceptance of the stub is equal to the negative value of the susceptance at point T. So what is the negative value of the susceptance at point T? That is minus 0.25. Minus 0.25. So this is minus 0.95 negative susceptance value, and this is negative susceptance value minus 0.95 minus 0.95 negative susceptance value, and extend this line. This line cuts the outer circular rim on the Smith chart. So that cutting point on the outer circular rim on the Smith chart is considered as a point C. This point is considered as point C. So at this point C, the wavelength scale is, and this is 0.37, this is 0.38. So approximately this point is 0.379 lambda. And this is the horizontal axis. In this horizontal axis, to the left of the, this is the left of the Smith chart. So the left of the Smith chart, on the outer circular limb, that cutting point is considered as a, and this is considered as a point A. And this is the right end of the Smith chart. This right end of the Smith chart at this point is considered as point B. So next, determine the length of the short circuited stub is calculated from the right side end of the Smith chart. At point B to the point C on the outer circle rim towards the generator. So this is called as length of the short circuited stub. So that length of the short circuited stub is denoted as L suffix T. So calculate this value. So therefore, the length of the short circuited stub L suffix T is equal at point C, the value is 0.379 lambda, 0.379 lambda, minus at point B, the value is 0.25 lambda, which is equal to 0.13 lambda. So in the Smith chart, at point C, the value is approximately 0.379 lambda, and at point B, the wavelength scale is 0.25 lambda. So therefore, the length of the short circuited stub is LT is equal 0.379 lambda minus 0.25 is equal 0.13 lambda approximately. So this is the procedure we can determine location of the stub and length of the short circuited stub from the Smith chart.